Assalamualaikum and a very good morning to everyone. Thank you for joining our second sessions of the MRC 2025 online sharing sessions. As for today's topic is about the open rocket simulations will be presented by Aina Sofea Fahizal, lead engineer of HEMREL. Without further ado, I would like to call upon Aina to share on today's topic. Aina.
Thank you, Farada. So my name is Aina, and I am the engineer in HEMREL. Can everybody hear me? Is that right? Yeah.
Yes.
Yeah. Okay.
Yes, yes.
So I'll share my screen. All right. Can you see my screen now?
Yes.
Okay. So we'll start right away. Just let me know if you have any questions. Basically, OpenRocket is an open source rocket simulation application. What that means is that open source, you can just download it for free. It's on the internet. Just search OpenRocket, and then there's a link for you to download it. So the aim of the OpenRocket is to simulate the performance of rocket before the fabrication and also the launch process. So basically, this is actually the very first step of you designing your own rocket. So what happens here is that you can choose the design in the sense of like the shape and also the length, the diameter, the shape of the nose cone, your fins, everything in OpenRocket. You can actually build your own rocket, the one you have in your head, and then put this into OpenRocket. And then you can also put in your rocket motor, and OpenRocket will calculate like the trajectory of the rocket, which means that how high it will go and the approximate velocity of the rocket itself. So OpenRocket is basically divided into three categories. The first one is the rocket design, where you build your rocket. And then the second one is motors and configuration. So here is where you will choose your motor, the motor that you want to use for your rocket. So in OpenRocket itself, there's like a very big database of motor that you can choose from. And then the last one is the flight simulation part. So in the last part, the OpenRocket will plot and simulate the graph for you. So you can see like you can what to expect from the rocket launch. Okay, so now we go to the basic components of a model rocket. So the difference between the model rocket and the actual rocket is on the altitude of the rocket. So model rocket goes only within the Earth atmosphere, but then an actual rocket will go out of it. So the very basic component of a model rocket, the first one is a nose cone. So this part is a nose cone. If you can see, it's always a little bit pointed at the front. It is never a right cylinder or a square because the function of the nose cone is to reduce the air resistance on the rocket. So what it does actually is just like, in a sense, it cuts through the air as the rocket goes upward. And then you have the body of the rocket. So the body of the rocket is the part that contains the rocket's engine and also the payload of the rocket, meaning that everything will be inside the body of the rocket. Let's say we have some sort of like telemetry system or the parachute. And everything will be inside the body. And then next we have the fin. So the fin control the direction and also the stability of the rocket during flight, meaning that the fin helps the rocket goes upward instead of going like unstable and haywire going everywhere. The fin will produce stability to make sure that your rocket go upward and can reach the altitude that you want. And then the last one is the engine. So the engine or the motor is there to generate thrust in order to propel the rocket into the air. So what happened is that as combustion happens inside the engine, fire and also smoke will go out from the engine, and then the force is strong enough to push the rocket upward. Okay, so that's on the basic components of model rocket. And now we can go to the additional components. So basically, this is like the very general components in a model rocket. So first we have the parachute. So obviously the parachute is a some sort of like recovery system. It is to slow down the descent of the rocket. So what happened is that after the rocket reached the apogee is basically the highest height that the rocket can go, and then it will start to fall down. So without a parachute, it will fall at a free fall speed. And what happened if it falls without a parachute is that as it hit the ground, it will completely shatter and be destroyed. So parachute is there to recover your system, meaning that you would not have a system that is completely destroyed. In a sense, um, you will also have a rocket that you can use again, and all the components inside, such as the telemetry system, can be saved. And then next we have the piston. So this is the piston. So what happened is that the piston is connected together with the ejection charge. So inside the ejection charge, there's some sort of like um, popping mechanism or explosion, a very small explosion that will push the piston out. As the piston goes out, the parachute also go out, and then the parachute will also push the nose cone go out. But the reason for the piston is to make sure that your parachute is safe. In some cases, we will use black powder as the ejection charge. But then, if there's no piston, it will burn the parachute. So even if there's a parachute, but then it's burned, then there's basically no recovery system for your rocket. And then next we have the telemetry system. So the telemetry system basically transmits, and also measures data such as the altitude of the rocket and then the speed of the rocket. In different cases, there's also GPS inside the telemetry system. So what happens is that if the rocket reaches um, altitude of about, let's say, 3 kilometers, so basically it can fall anywhere in the radius of 3 kilometers. So the odds of you knowing where to find it is very low. So that's why we need a GPS inside it. And then there's the connector. So basically this is the connector. If you can actually see, there's like two different component parts of the rocket body. So this is the lower part, and then this is the upper part. So the lower part basically contain only the motor and also the fin, and while the upper part contains everything else, such as the telemetry system, the ejection charge, and then the parachute. So connector connect them together. And then you have the launch lug. So if you can see like a very small rectangle here near the fin, is the launch lug. So what happened is on the launch itself, you will have a straight, some sort of like stick to keep the rocket upright. So the launch lug will provide the stability for the rocket prior and during the liftoff. So what happened is that you connect the rocket and also the launcher through the launch. Okay, and then last one, you have the centering. So centering, basically, if you see the body is slightly bigger than the rocket itself. The gray thing, this is the rocket, in your motor, your engine basically. And then this is slightly smaller than the rocket body. So what we do is we add a centering. So centering is basically just a small cylinder of like 3 centimeter, 2 centimeter with a hole inside it, and then it keeps the motor rocket center inside the rocket lower body. Okay. Is everything all right? Everyone all right? So for the Opal rocket design. So first, when you open your Opal rocket, this is your main page. So if you can see, there's 3 categories here. The first one is the rocket design, and then the motor and configuration, and lastly is the flight simulation. So basically, this is what the 3 categories that I told you about on the first slide. So underneath that, if you can see, there's a rocket with a sustainer. So this will be all the parts of the rocket that you've added shown. It will be shown here. So you can, afterwards, when there's everything is complete, and then you suddenly want to change, let's say, the nose cone. So you can just like select nose cone and then add it from there. So this one is where all the components are. So you can see the nose cone, the body tube. And then on the bottom part of the main page, you can see this is where your rocket design will be located. So there's also additional information for you, such as the stability of the rocket, and then there will be the rocket length and the diameter of the rocket, as well as the mass of the rocket. And then lastly, on the bottom side, there's the apogee, which is the highest altitude, the possible highest altitude. So this part, the blue part, will only be there if you have already add your motor. So here's the options of tasks, just like what I told you guys. So the first part should be the rocket design. And after you're done with the rocket design, you can go and select your motor. And then only after that, you can do a flight simulation. So these are all the available components. If you can see the shaded gray, this one, this is the fin, the trapezoidal fin. And then there's also like elliptical fin. And then if you want to design your own fin, there's also fine. So there's a free form. It will give you like a grid, and then you get to decide the shape of your rocket, the shape of your fin. So, and then there's tube fins if you're feeling adventurous, wanting to try it. Also, the launch lock. So basically, this is the one that will connect the rocket and also the launcher. Okay, and then you have the inner component of the rocket. So first, you have the inner tube. The inner tube will be the thing that will hold your motor. So if you want to add your motor, it is only possible if you add your inner tube. And then after you choose your inner tube, meaning that your sizing and also your diameter and length, then only can you add your motor. And then you have your coupler. So the coupler is basically the same thing as the connector. You can just add this to connect the upper part and the lower part of the rocket. And then next you have the centering. So this is basically just like what I told you guys. The centering is the thing that holds the rocket motor to make it center. And then there's a bulkhead. So bulkhead is located above the rocket motor. So what happened is that bulkhead prevents the any fire that could happen, meaning that when the combustion happens, there's a slight chance that the fire will go upwards. So in order to prevent fire from reaching your other payload, such as your telemetry system, your parachute, the bulkhead is there. Same goes to the engine block. So, but then the engine block is like a bigger. So you put the bulkhead first, and then you put the engine block. So engine block protects like the whole engine part. So that one is located on the bottom, the lower part of the body. And then you can also add your mesh objects, so such as parachute. Parachute is already there, meaning that when you want to add your parachute, you can just click on this and then it will be there. You just have to select the sizing of parachute, meaning that your diameter of the parachute and the length of the parachute. And then there's also trimmer, but most of the time we don't really use this one unless if you want to add like additional components to your rocket. That's fine also. And there's a shock cord. Basically, what shock cord do is shock cord connects the parachute and the rocket. So basically, you can tie the shock cord between the parachute and also the nose cone of the rocket for you to make sure that it doesn't get lost. So what happens is that when it falls, you will find your whole rocket together in one component. Okay, so basically there's no other components such as telemetry and also ejection charge. So that part you can just add by adding the mesh component. And then you can click this one and then there's like a bunch of um available options that you can choose from. Okay. And then so yeah, just like I said it just now, this is where the rocket that you have designed will be displayed. Okay, so first, when you wanna design a rocket, the first thing you should put is your nose cone. So when you double click on the nose cone, there will be and like some sort of like edit button, edit options right here. So there's a component mask, component component one, and then here is like the general detail of the nose cone. So first, there's like a bunch of shapes that you can choose. It could be ogive or ellipsoid, and then shape parameter. And then there's a node cone length. So this one you can play around and just like select the length of the nose cone that you want. And also there's like a base diameter for the nose cone. Also the wall thickness. So basically, why you need to give all this information is that because after you select all this information, that is the length, diameter, and thickness, you can choose also the material of the nose cone that you want. So after you also choose the material, OpenRocket can calculate the mass, the approximate mass for your rocket. Meaning that for the nose cone, it can calculate the mass using the volume and also the density of the material that you want. So you can just play around with the shapes, diameter, length, and also materials of your rocket. Doesn't have to be like absolute or jive or whatsoever. And then next, there's like additional informations for the rocket component. So there's shoulder. What happened is that shoulder gives you the part where there's like an additional part connected to the rocket nose cone that help it to fit inside the rocket body. And then there's like a override. So override, you can override the mass. And then appearance, you can basically like change the color or whatsoever. And then there's just comment in case if like you want to share this file to other people, they can see the comment what you have to say about the nose code. Okay, next. So what you do after nose code is you just add your main components. So here I I've added my rocket body. So this is the upper part. And then you have your lower body. And then on the lower body, I've put on fins also. So this is a basic trapezoidal fin. So right away, Opal Rocket will calculate the length of the body that I want, of the rocket that I want, and then the maximum diameter of my rocket. It will also calculate the mass of my rocket without any motor. Okay. So if you can see here on the right part of the screen, it's there's a information on the stability. So basically, the stability is affected by the position of the center of gravity and also center of pressure. Center of gravity is basically the mass distribution of the rocket itself. And like this is the center of mass for the rocket. But the center of pressure is basically um, where the pressure of the rocket is zero. But this is basically the center of pressure is not something that you have to calculate yourself or whatsoever. This is something that the upper rocket will approximate you. So it will give you the approximate center of gravitation and center of pressure. So okay, so if you see what happened was the rocket was unstable. So instead of like going upright and then reaching the one, it started to go haywire. So some of the factors that affect the rocket stability is that the distance between the center of gravity and the center of pressure of the rocket. So, meaning that if the distance between the center of pressure and the center of gravity increases, the stability also increases. Meaning that more distance between them, more distance between them, then you will get a higher stability. But then, very very large margin, meaning that very large distance will give you a rocket that is overstable, meaning that it is too stable. So what happens when the rocket is too stable is that it is very sensitive to like wind. And then when it's sensitive to the wind, it will reduce the performance of the rocket itself. So ways for you to increase the rocket stability is basically just to play around and change the body length of the rocket. And then you can also change the length of the nose cone or fins, meaning that you can also change the number of fins, shape of fins, the length of the fins itself, and then you can play around with the diameter of the nose cone, and then maybe change the shape of the nose cone itself. And then, so everything will affect the rocket stability, meaning that you add more weight, it will affect your stability. And then you reduce your weight, it will also affect your stability. So the stability margin will always change, meaning that later, so basically, um, the stability of the rocket is calculated right away. But then when you add your motor, it will basically add weight on the lower part of your body as weight increases. So it will slightly reduce your rocket stability. So make sure to evaluate the rocket stability before proceeding to the next phase, meaning that while you are designing your rocket motor, the rocket design itself without your motor, give it a slight higher stability. So basically, a stable margin ranges from 1 to 5 to 3, as higher margin would cause the rocket to be overstable, just like what I said just now. So basically, just give it a slight higher stability on the designing part, because when you've added your motor, it will decrease the stability slightly. So just make sure that you can still be in the range of 1 to 5 to 3 in order to have like a stable rocket. But then again, um, it will the stability of the rocket that is calculated by the Opera rocket would not give you the ultimate verification of like how the direction of your rocket will be. Meaning that sometimes you can also have an overstable or like unstable rocket, because Opera rocket is basically just an approximate assumption on how the performance of the rocket will be, but there's no right answer for it. Okay, and then we can go back to the next after you've added your everything basically. So on this part, I've added my nose cone and also upper part of the body and the lower part of the body. So next, I want to add my inner tube. So just like what I said, the inner tube is where your motor will be located. So see if you can see here while adding my before adding my motor, my stability is on quite the high range, which is 2.9. But then it's okay because adding the motor will add more weight and will affect the stability of the rocket itself. So the rocket engine placement is usually located on the bottom part of your rocket. Fire will go out from there. So we don't want any of our components to be destroyed due to fire. So we put it downward. Okay. And then after that, you you can add your motor inside your rocket. So after the rocket design, you go to the motor and configuration. So the motor mounts, if you can see here, you choose the inner tube. So basically, this is saying that you're going to put your rocket inside the motor inside the inner tube. So after you've clicked the inner tube, it goes that here it will be none, no motor. So now you can select a motor. So just like what I said, there's like a very large database of motor inside Opera Rocket. So you can just choose from here to have like the approximate power of your rocket, basically. So the rocket is classified based on the total impulse. So the total impulse is basically the force in Newton second of the force itself. So there's like a class A, class B, up to class O. The higher the alphabet order, the higher the power of your rocket. Meaning that now class O is the strongest rocket in a sense. There's the analogy. Since there's like a large database, you can like narrow it down by sliding this to choose the class that you want. So when I put the right one on C and the left C and O, so basically that Opera Rocket will give you data from motor that is in class C up to class O. And then you can also like limit narrow it down more into the motor dimensions. So this is basically the diameter of the motor you can choose, and then also the length of the motor. So it helps you find the motor faster. And then, yeah, so basically this is what it is. So factors of selecting rocket engine is the total impulse and also the motor dimension, meaning that you want a motor dimension that can fit inside your inner tube and also can fit inside your rocket body. You don't want a motor that is bigger than your rocket body. So the total impulse, higher total impulse basically will give you higher flying rocket. It means that it can reach the higher altitude. So the class of the rocket engine determines how high your rocket will go. So this is all depending on the amount of impulse. So it's like I said, a greater impulse results in a higher altitude of the rocket itself. And then after you have if you selected your motor, so if you can see, before I put my motor, my stability is on 2.9. But now after I have put my motor, my stability decreases to 2.63. And then after you've put your rocket motor, you can see that Oppo Rocket already calculated your R4G, which is the highest altitude that your rocket can go, and then your max velocity, which is the highest speed your rocket can go, and also the maximum acceleration of your rocket. Okay, and then if you go to the third part of the Opera Rocket task, the flight simulations, you can simulate a new simulation, a new flight. So simulation one, you just click on this and then you can edit your simulation. So basically, if you know the exact place that you want to launch a rocket, you can change the average wind speed, the standard deviation of basically the wind, and then the turbulence intensity of the place. And then there's also like a wind direction for it. But then you can also select your latitude and longitude of the launch site. So all of these are like added information that you can add to make sure that the approximation is nearer to the exact performance of your rocket on the launch day itself. And then you can then simulate and plot your graph. So what happened is that next, Opera Rocket will ask you the type of information you would want. So the default one is the altitude, which is the height of the rocket, the vertical velocity, which is the velocity of the rocket going upwards, and the vertical acceleration of the rocket. So this is the default one. Most of the time, we'll choose the default one. So we'll just click plot. But then in different cases that you want to study different information, you can also select that. So after you click plot, basically OpenRocket will plot your flight for you. So if you can see, the red one is the altitude. So this here is the highest altitude of rocket. You can see it goes up 450 meters at time 6 seconds. So basically the rocket flies at zero and then it goes up until at around 6 seconds it reaches its highest height and then it starts going down. You can also see the vertical velocity plotted in blue. So you can see that the velocity, the highest velocity, uh, is reached at around 2 seconds. And then there's also your vertical acceleration. So all of this you can like try and error and study yourself. Basically, if if you move around on the plot itself, it will give you the range at the exact value at this particular second. What is the exact altitude of it? And then at this particular second, what is the exact vertical velocity of it? Okay, so basically that is all on the Opera Rocket flight simulation. But then I think I'll show you guys like how to actually do it on Opera Rocket itself. But then I think we'll take five first. Is that all right? And then we'll continue. I'll show you how to actually do it in Opera Rocket. Is that all right for everyone?
Do you guys has any question to ask Aina? You can ask directly or in the chat box regarding to this topic.
First question, can we get the meeting recording without signing it? Not very sure on that. Maybe I'll check back with Farhana on how she will give to you the recording, and then I'll let you know. So the second one is what is maximum requirements length or diameter of the rocket. So basically, so for this particular competition, we will give you the rocket body, meaning that unless if you want to do it yourself, there's no actual requirement on the diameter. But it just needs to be bigger than the diameter of the motor itself. Last year, the diameter of the rocket body that we gave is 76 millimeter. So that's on the diameter of the rocket. But then there is no limitations on the length of the rocket. So whatever length that you want to make, you can make it longer, you can make it shorter, whatever, as long as you can fit every other components inside the length of the rocket, and also make sure that the rocket is stable. So yeah, that's that. Does that answer your question, Arif? So I think now we can continue with the how about the motor? Uh, I'm sorry. What about the motor? Meaning that the diameter of the motor, is it? Okay, so basically the length of the motor is approximately 40 centimeter, and diameter of the motor is around 50 mm. But afterwards, we will give you like the exact dimension of the motor. After we've like um settled everything down, like, so I will give you the exact. So for now, the length is around 40 centimeter and the diameter is 50 mm. Is that right? I hope that answers your question. So next, I guess I'll show you how to um, basically design on your Oppo Rocket. So I'll share my screen. So I hope you can all see my screen right now. So basically, it's like what I've showed you guys on the slide before. There's like a selection of tasks for your rocket. So there's a rocket design, there's model and configuration, and so the flight simulations. And then this is where all your components will located. This is where you will select all of the components. And this is where your design will be shown. So first thing first, you select your node. And then so ultimately the option details will go out. So now, so for the node square shape, there's like a different shape. You can select conical or maybe ellipsoid, or there's like a power series and then the parabolic series. This will give you different type of node square itself. So I would like to go with the ellipsoid one. And then for the length, I would like, so this is a very random design, meaning that now I just want to show you guys. There's no mission for it. But unlike for you guys, you would want to have a rocket motor a rocket that can reach up to 1 kilometer. Meaning that we'll give you all the details on the motor. All you need to do was design the rocket. But then for now, I just want to basically play around, show you guys how to achieve the stability of the rocket. So the length, I would like for it to be around 10 centimeter and the base diameter of 5. Wouldn't change that. And then there's the wall thickness of 0.2. I would just let it go. Just let it be. And then the component, I would change it to, basically, I am printing my nose cone. So I would like for it to be PLA, which is the filament of my 3D printer. And then the component finish will be just regular paint. So ultimately, the Oppo Rocket will calculate the component mass of the nose cone. So this is 32.7 grams. And then I would like also to add shoulder to my nose cone. So I'll add a diameter of, basically this is the shoulder. So it has a length of 1 centimeter. So let's see that my rocket body has the inner diameter of 4.8. So I would like the diameter of my shoulder to fit perfectly inside my rocket body. So you put 4.8. And then thickness, it's up to you guys. If you guys want to make it like whole, so this will add mass to the nose cone itself. You can see when I put thickness at 2 centimeter, the mass is 54.7. But then when I decrease the thickness, the component mass also decreases. Okay, that's that. So I'm done with my nose cone. And then I would like to add my body tube. So this will be my upper part of the body. This is my upper part of the body. So I would like to edit it. So let's see that the length of the upper body, I would like to make it around 20 centimeter. And the outer diameter is 5 centimeter. Basically, this is the same diameter with the nose cone itself. And then the inner diameter, I would like to make it, the inner diameter is 4.8. I would want it to fit perfectly with my nose cone shoulder. The inner diameter is 4.8 and the wall thickness is 0.1. And then the material, basically you can also change it, up to you guys, but I would want to stay with cardboard because I want my rocket to be made of cardboard. And then so there's also like other different motor mount configuration. So this is if you want to put your motor inside the body tube. But yeah, ada question ke? Okay, so this is if you want to put your motor inside the body tube, but we don't want it because this is the upper part of the rocket body. And then there's also an override. So basically, if you add override, instead of using the mass component that the rocket motor, the upper rocket calculate for you, you can change it to the actual mass of the body. So in case it's like you have already have the rocket body, so you can weigh it and then put the actual mass. So let's say that the mass is around 35 grams. So the body tube, it has been, the mass is already overridden to 35 grams. So that's that. And then I would like to add the lower part of the body tube. So basically the lower part of the body tube only contains the rocket motor. So it's gonna be much smaller. I would like to make it around 5 centimeters or maybe 7. Okay, and then the outer diameter, just let it be. But then basically the lower body tube is the same exact materials with the upper body tube. So my upper body tube inner diameter is 4.8. I would like to change it also. And then I let the wall thickness be that. And then the component material is 0.68. That's the density of the cardboard. Okay, so that's that. So on the body tube, the lower part of the body tube, now you can add your fins. So let's say I would want to add an elliptical fin. So as you can see, it automatically adds your fin right there. So you can choose between the number of fins. So I would like it to be 4 fins. And then the root cord basically is the length of the fin on the body tube. So this is the root cord. Meanwhile, this is the height of the fin itself. So I would like to increase my root cord. Let's say I make it 6. So what happened is that if you can see, every time I change any information on any of my body parts, such as the root cord, so right now it's 6 centimeters. You can see the stability is 1.9. But then if I decrease it into 5 centimeter, you can see the stability increases to 2.04. And I could also change the height. So this also increases the stability. Okay, maybe I would want the thickness to be thinner. So let's say 0.2 centimeter. And then just like before, I would want the material, I would want to print my pin. So I would choose the material that I'm using, which is PLA. And then basically it gives you this whole thing. So this is the basic component of the motor, the basic component of the rocket itself. You have your nose cone, and then you have your upper body part, which will contain your parachute and other components. And then you also have your lower body part, which contain your fins and also your motor. And then so next, I would like to add my motor. But then before that, as you can see, as I've put all these components, rocket open rocket give me the length of my rocket itself, and then the maximum diameter of my rocket. Also with the mass of my rocket without motor. But it cannot give me the apogee or the max velocity of my rocket yet because I haven't added any motor. So how do I add motor inside my So how do I add my motor? It's basically just click on the body tube. So the inner part in the tube will be located inside the lower body tube. So just click on the inner tube. So now, just like just now, you can choose the size of your inner tube. So I would like it to be a little bit bigger. So the diameter is around 2.9 centimeter and the inner diameter is 2.8. And then the position, the placement is located at the bottom of the parent component. So basically the parent component of this inner tube is the lower part, the lower body tube. So if I change it, meaning that if I increase +1, it will go downwards. But then 0 will make it perfectly at the bottom of the parent component. And then as always, you choose your material that you want. So I'll stick with cardboard for now. Okay, and then once you have your inner tube, and then only you can go to motor and configuration. So you select the inner tube, right? And then you can see that there's no you cannot select your motor yet. Okay, let's see what is wrong. Tube and this so this is the motor mount. Okay, this person can over each flight. Basically, this is where you will put your motor. Okay. Okay, so now you go to the new configuration and then now you can select your motor. So if you can see the length, this is basically a very small rocket. It's only like 38 centimeter. So let's go with, if you remember your inner tube size, basically my inner tube length is around 70 mm. So let's go to the length of 70. This, everything gives you 70 mm length. So this limit it to 70. And then if I remember correctly, my inner tube is around 2.9 centimeter. So we can select a motor that is, so here is a 24 mm. Around here is 24 mm. Let's select the highest total impulse. So higher total impulse will give you higher power, meaning that higher altitude the rocket can go. So let's select this Aerotech 50 Newton second total impulse and with a diameter of 24 mm and the length of 70 mm. So select that one. So it goes right away inside here. Now, if you can see, it gives you the details on the apogee of the rocket, which is the height. So this rocket can go up to 533 meters. And then we can also give you the max velocity of 204 meter per second. So basically, this is a very fast rocket. and then the maximum acceleration of 357 meter squared, meter second squared, meter per second squared. Okay, so now we're done with the motor addition. But now let's see on the stability of the rocket. So if you can see, if you remember, before I add my motor, the stability was around 2. But then now that I've added uh, a very powerful rocket for this class, the stability goes down to 1.14. So basically, this is below the range of the stable rocket. So we would want it to be higher, the stability. So let's try to go back to the rocket design and then try to change to play around with maybe the length of the rocket to increase the stability. So let's say that I increase the length of the lower body. So if I increase, the stability goes up slightly. And then let's play with the fins also. Let's say I decrease the number of fins, so it will decrease the stability. But then when I increase, it will increase the stability as well. So let's say I add 5 fins. So this also increases stability. And then let's increase the root chord. Okay, so basically increasing the root chord of the fins decreases the stability. Go back to 5 centimeter, and then let's change the height of the fins. So maybe make it longer. Yeah, so we can see it's already 1.48 stability. And then let's increase the length of the nose cone also. Okay, now I've increased the length of the nose cone to 12 centimeter. You can see the stability is 1.54. So this falls under the range of the stable rocket. Actually, you would want a much stable rocket, which ranges from 1.5 to 3. So this is barely above the stable range. So maybe a stability of 2 or 2.2, 2.3, that would be like a very stable rocket. Okay. So basically, when you add all these components, when you play around, let's just like what we did just now, I increase the length of the lower body tube, and then I increase also the length of fins as well as the number of the fins, as and also the length of the nose cone. You can see that from 533, you can see the apogee decreases to 477. So what happened was that as I increase all those stuff, as I play around with all the stuff, there's an additional weight from it. So more length mean more weight. So more weight reduces the highest altitude that your rocket can go. Okay, so now we're done with the rocket design and also motor configuration. Let's go to the flight simulation. So basically, OpenRocket has already simulated a graph for me. Let's just click run simulation. Okay, so basically this is the basic default settings. So the x-axis is the time, and then the y-axis is the altitude. You can see there's all these different information that you can get. Basically, there's a total velocity, total acceleration, position east of launch. There's also the lateral distance of the rocket, the lateral direction of the rocket, and then like a latitude, lateral acceleration, the gravitational acceleration, and all this stuff in case you want to study it. So you can just select it. But I'll just go with the default one, which is the altitude, the vertical velocity, and the vertical acceleration of the rocket. So let's click plot. So now, there you go. There you have your simulation. So this is your altitude. So let's say it starts at 0 second. So at 0 second, the altitude is barely so 0.089 meter. And then at around um nearing 8 seconds, it goes to the altitude. So basically the highest altitude for the rocket is around 482 meters. This is at 7.79 seconds. So there you get your highest altitude. But then after that, it starts slowing down. So now you can see also the vertical acceleration. So at 0 second, and then the highest velocity, the yellow one, you can see the highest velocity is at around 1.09 seconds. So this at this time, the velocity is 189 meter per second. And then after that, it starts going down. The same goes to the acceleration. So the maximum vertical acceleration is around 328.79 meter per second squared at 0.1 second. So right away after it launched, and then after that it goes down. Vertical acceleration goes down, and then after it reaches the highest velocity, it starts going up again before it goes through some sort of like a free fall, but with the recovery. So, free fall basically because we don't have any parachute until it reaches the ground at 21 seconds. Yeah, so that's mostly all the things that you can learn about from Open Rocket. So yeah, this basically helps a lot with the all the designing part. So before you fabricate your rocket itself, you design it inside Open Rocket, and then you can have a slight idea on like the shape and the length and the diameter of the rocket itself. So what why is that? Is because um you don't want your rocket to be like a total disaster after fabricating it without designing it inside the Open Rocket first, without any simulation. You don't know if your rocket is gonna work or if it's gonna go upright and stuff like that. Yeah, so I think that's about it on Open Rocket. You can just basically, since this is an open source apps, you can just like watch videos on YouTube to learn more on the Open Rocket software. Yeah, so I think that's about it. If there's any question, please just ask away.
Do you guys has any question to ask about today's topic? You can ask on the chat box or directly to Aina. I guess there is no questions on today's sessions. Uh, I have shared the attendance links on the chat box. As for today's session, we will be sharing the HEMREL YouTube channel. So please do follow us on our YouTube account. Thank you for your time today. Our next sharings on Kansai satellite is on 14th June. See you guys on the next session. Thank you.
Thank you, everyone.